Hello, my name is Eliza Simandera, and this is my lab report for the fourth lab, Oscillations. The purpose of this lab was to compare the observational and predicted paths of a spring mass system. The concepts that were applied in this lab were Newton's second law of motion, which states that the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass, and the energy principle, which states that the net work done by all forces acting on a particle equals the change in its kinetic energy. The equations used were the gravitational force formula, the velocity update formula, the position update formula, the spring force formula, the kinetic energy formula, the gravitational potential energy formula, and the spring potential energy formula. The lab gave us a video of a spring and mass oscillating, so performing the experiment was not necessary. I uploaded the video into the tracker software. Once it was calibrated and the axes were set up, I tracked the mass's position frame by frame. This resulted in data that I graphed in Excel. I then used GlowScript to create the projected graph with the velocity and position update formulas. To analyze the results, GlowScript automatically combined the data from the video with the predicted paths. This is a video that was given of the mass oscillating. This is a screenshot of the tracker software that was used to create the position versus time graphs. As you can see, the spring was used to calibrate the tracker, and the purple lines are the axes. The red diamonds following the mass's path are the position points. They were recorded frame by frame as the mass oscillated. As you can see on the right, the graph was made in the software and the data points are all below. This is the GlowScript code. The highlighted boxes are lines that I specifically changed. Most of the values found were from the pre-lecture video. First, I set the mass to 0.402 kilograms. I then set the mass's initial position to the first data point. I found its initial velocity by finding the average velocity between the first two frames of the video. I set the spring constant to 6.83 Newton meters and the relaxed length of the spring to 0.123 meters. I set the length of the spring to be the difference between the mass's position and the spring's position, and set L hat to be the length vector divided by the magnitude of the length. I set S to be the difference between the magnitude of the length vector and the relaxed length. I then filled in the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy formulas. In the calculation loop, I first set the initial values, which will be used in calculations later on. I then calculated the gravity and spring forces and combined those for the net force. I update the mass's velocity and position vectors with the velocity and position update formulas. I update the spring's length variables with the same equations as before. I also update the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy with their respective formulas, and calculate the difference between the new value and the initial value that was stored at the beginning of the loop. After inputting the observed data and running the code, I got these two graphs. As you can see, the x position versus time graph is a lot closer together for the model and experiment data, while the y position versus time graph is a lot farther apart. This discrepancy can be noted to multiple things. First, this was not a perfect system. This means that air resistance likely slowed the mass down. There was also work done by the surroundings that isn't accounted for in the GlowScript model. There also could have been human error when tracking the video, as the position points may not have always been perfectly placed. The first discussion question asks if the energy principle is satisfied. I would say it is satisfied. Because no external forces are acting on the system, the change in energy is zero. You can see this change in energy with the orange line on the graph on the right. The second discussion question had us estimate the oscillation periods from the x position and the y position graph. I first found the x direction oscillation period by finding two peaks and calculating the time difference between the two. This resulted in 1.614 seconds. Doing the same for the y position data resulted in 1.519 seconds. The x position's oscillation period is about 0.1 seconds longer than the y position's, which isn't a very large difference. Thank you for listening.